Let me briefly say something about trees. These are, again, a special type of graph. So a tree is a connected graph with no simple circuits. You might also, another way to define a tree is a connected graph with no cycles. Either definition is fine with me. So it's a connected graph with no simple circuits or cycles. For example, here's a tree. There are no simple circuits in this graph. This graph is not a tree. Why? There's a simple circuit right here, this triangle. So it is not a tree. Another tree, probably the tree that you're most commonly familiar with, is the binary search tree. Again, no simple circuits in this graph, and it's connected, so it's a tree. So a leaf is a degree 1 vertex in a tree. Okay, so for example, even though this is a tree, this vertex right here is not a leaf. It has degree 1, 2, 3, 4. These vertices, this one, this one, this one, this one, this one, they're all leaves. In this binary search tree, this is a leaf, this is a leaf, this is a leaf, and this is a leaf. Any vertex with degree 1 is a leaf. Here are two really simple properties of trees that are true. I'm not going to prove it for you, but your book does discuss it, so if you'd like to look it up there, you can. Fact 1 about trees is that a graph is a tree if and only if there exists a unique simple path between any two vertices. Okay, so if you give me a graph and you tell me that between any two vertices in the graph there's a unique simple path, then I know it's a tree. And if you tell me that it's a tree, I know that for any two vertices that you pick, there's a unique simple path between those two vertices. So these are two equivalent properties. So having a unique simple path between any two vertices is equivalent to being a tree. And fact 2 is that for any tree, there exists a leaf. So if you give me a graph and you tell me it's a tree, I know that there has to be at least one vertex that's a leaf. So now what do we want to prove? Well, we want to prove the following claim. Any tree with n vertices has n minus 1 edges. So for example, this tree has 1, 2, 3, 4, 5 vertices, and you can see it has 1, 2, 3, 4 edges. So we want to prove that for any tree with n vertices, it always has n minus 1 edges. How do we prove this particular claim? We're going to use induction. And we'll let P of n be exactly as above, any tree with n vertices has n minus 1 edges. What's the base case? The base case is p of 1. If you have a tree with one vertex, then it has 0 edges. Yes, that's true. And now we need to show that for all n, p of n implies p of n plus 1. So we can assume that p of n is true, and we need to prove that p of n plus 1 is true. Okay, so what is p of n plus 1? P of n plus 1 says any tree with n plus 1 vertices has n edges. Okay, so let T be a tree with n plus 1 vertices. Call that step 1. We need to show that T has n edges. That will conclude P of n plus 1. So by fact 2, that simple fact 2 from the previous piece of paper, T has a leaf. It could have more than one leaf, but it has to have at least one leaf. So let V be a leaf of T. Okay, so we have this leaf V, and it's connected to some other part of the tree that I'll call T prime. Okay, so here we found some leaf of T, we've called it V, it's connected, since it's a leaf, it has degree 1, so it has one edge connecting it to the rest of T that I'm calling T prime. So how many vertices does T prime have? Well, we removed one vertex and one edge, and we looked at the rest of the tree and we called it T prime. So T prime is missing one vertex and one edge. So T prime has n vertices because we're removing this leaf. So by the inductive hypothesis, T prime has n minus 1 edges. So there are n minus 1 edges sitting here inside T prime. So now we can calculate the total number of edges in T equals 1, which corresponds to this edge. So this edge right here, that's 1, plus all of the edges inside T prime, which we just said by the inductive hypothesis is n minus 1. So this equals n edges. So therefore, the total number of edges in T is n. But look at P of n plus 1. We wanted to show that T with n plus 1 vertices has n edges. And we did just that. We showed that the total number of edges in T is n. So this proves P of n plus 1, and it completes the proof. So we've shown by induction that any tree on n vertices has exactly n minus 1 edges, and we'll come back to trees a little bit later on in the course.